look to see, we look to predict the height of rise as a function of the tube size and the surface tension and the density. Now we'd like to try and look at the dynamic situation. So how is it that how does the speed of the meniscus evolve as a function of time? Okay? And so if we just run this again, look at the guy on the right, I think it's pretty clear that it's slowing down as a function of time. It's going really quickly then. Okay, so we want to be able to rationalize this. And so this is a problem. This is a nice example of mathematical modeling. But with all mathematical modeling, you can get so lost in detail that it becomes uninteresting. Yeah, Friday's a holiday? Woohoo! Okay, good. Friday's a holiday?
Better example here.
So problem set will be due on Monday. Okay, so I was just saying the perils of mathematical modeling is you can get too lost in detail and worry too much about it, and then it becomes physically uninteresting. So I'll try and capture three regimes. There are actually more regimes that can be obtained in various asymptotic limits, but I'll try and highlight the three of interest, of greatest interest. So we saw last time so the equilibrium rise height okay. So now let's look at the approach to this steady state. Okay, so we have to try and enumerate all of the forces. Can you see this? You see? Okay, so if we consider this fluid column, let's call this surface S4. So we have a little surface here. We want to look at all of the, we're going to do a free body diagram on this chunk of fluid. Okay? So this chunk of fluid, we're going to call this height Z. So the mass so mass is going to be, so this is going to be a function of time. So the rate of change of momentum is going to be equal to the total forces acting on the column. And we can expand this right away. Okay, so this has to be equal to the sum of all forces acting on this fluid column. Okay, so let's write them down. The first is we know that there's a tensile force acting in this direction, which gives rise to a vertical component. Okay. So that last time, that's basically the line tension integrated around the contact line. Okay, so that's acting vertically. We have the weight of the column. Okay, we have, so what else do we have? Okay, so if this thing's moving upwards at speed z prime, that means that there's a flow in here, which is about z prime, which means that this region represents a Bernoulli low, right? So the pressure is low here by an amount rho u squared, right? Half rho u squared. So that's a force acting on being felt by the base of the column, which is retarding the motion. So this is dynamic pressure. Okay. There are also going to be viscous stresses as this thing moves along here. It feels the walls, and the walls are going to slow down the motion, particularly when the motion becomes slow. Okay. So 2 pi a, so that's the surface area times the viscous stress. And there's one more. So what if we have fluid shooting in here? So we've seen what the dynamic effect is. The effect of the dynamic pressure is to slow it down. But also we know that if an object is moving around and it's shooting fluid out, then it's going to accelerate, right? This is momentum flux argument. And so here, so in general, you have to integrate the flux going into a fluid volume. And here the flux is coming in to the base through the surface S4. So this is the momentum flux term. So again, if you think of a rocket, it's ejecting fluid outwards and there's a resulting force acting on it. If you calculate this, so this is V is in the vertical, so this is basically Z. This is basically, let's write this, is pi squared is the area, and then it's just rho z prime squared. So that basically cancels this guy. Okay, and so the last thing we want to do, so we can make an estimate. The magnitude of the viscous stress is going to depend how developed the flow is. We know eventually when we have flow into a tube, eventually you get Poisson flow. So when the vorticity is diffused in from the walls completely, then you get a parabolic flow. So that can give it, if we assume that the flow looks like that, then we can get an estimate for the viscous stress. So it's parabolic, looks like this. So it basically goes to 0 on the walls. So the stress on the wall. Okay, so this gives the right flux. So if you integrate this across the entire tube, and the stress on the wall Okay, so this is again only going to be strictly true if you have a parabolic flow, but it'll allow us to make an estimate for tau nu. And so what we want to do is we want to look at various regimes where these various forces are in play. Okay, so if we take our master equation now, we sub in here. Just to indicate that that's not a tensor. Okay, then we get the following. Okay, so that's about as complicated as we need to get the most of the physics. So this is basically the inertia of the column, surface tension, dynamic pressure, viscous stress, and gravity. Okay, so I have cut a few corners just because I thought you guys it would bore you if I did more. But you can also, there's another thing that you can worry about is the added mass. So basically as the thing goes into motion, there's flow in from around here, and that contributes to the early stages. But we're just going to bin that if you want to be they say things can make things as complicated as you like. But notice that we know that in the final balance, we have this balancing this, right? And that sets the final rise height. The question is how we get there. Okay? So we can now look in the various regimes where each of these forces is important. Okay? Okay, so the dynamics in any particular case is going to depend on the viscosity. So whether this term dominates, for example, this term, or this term. So let's look. And also we know that at the early stages, Z is going to be approximately 0. Okay, so we're not going to have to worry about that one in the early stages. So let's look at the we expect there's going to be a time scale for viscosity to diffuse across the tube, and this is going to be basically again, if we think of dynamic viscosity as being a diffusion of vorticity, then we know that time scale is going to be the tube radius squared divided by the viscosity. So it's going to scale as a squared over nu. So that's, again, simply the time it takes for vorticity to diffuse in from the side. So you get flow in a pipe, and it's at time t equals 0, you force fluid through the pipe. Then initially it's going to be slug flow inside. You have a no-slip boundary condition, and then as the flow evolves, the boundary layer thickens until eventually you get this Poisson flow profile. You basically get. Okay, and so it's literally a matter of how quickly this boundary layer grows in from the walls. Okay, and so again, if we think in terms of the diffusion vorticity from the walls, we expect this time scale. So at early times, you basically have slug flow, and viscosity is not important. So we have then the what's that? Slug flow means the whole thing's just moving. The profile is flat. So basically, the whole thing's moving at the same speed. And then in the viscous limit, it's Poisson flow.
The one I forgot, why do you mean slug?
Slug just means just moving, the whole thing's moving together. So slug flow means, and not slug the animal, a slug of fluid. Yeah, slug of fluid is just so if you have a tube and it's not feeling the boundaries, then a slug of fluid, if you start with a cylindrical slug of fluid, it will still be a slug of fluid as you move down. Whereas, yeah, exactly right, yeah.
Yeah, and then also the Poisson and good for fluids that have a reasonably
High viscosity. Right. The long.
If it's just the longer it rises, the better is the plus oil.
Yeah, that's right. That's exactly right. Yeah, yeah, because it'll take a certain amount of time. So to get to the viscous, yeah, the longer it goes, the greater the chance of it's getting to Poisson flow before it stops.
So
Yeah.
it's less viscosity.
Yeah. Okay, so if we're in the inertial regime, that's where viscosity is not important. So basically, for times t less than t star, and also, so we're looking at the initial time. We know that z is around 0, so we're basically looking at the motion when it first starts. Right, so the thing is basically moving like a slug. You just have a thin boundary layer on the sides. Okay, so viscosities. Okay, so the rise, we know it's being driven by capillarity. So we have a balance between these two. So it's being balanced basically by the dynamic pressure. Okay, so that's our first regime. We see that the speed is constant. Okay, and that's going to be, so that's independent of viscosity and gravity. So that's basically how things start. And then as things evolve, this term is going to become important relative to this term. We know we're eventually asymptoting to a balance between these two. Okay? Okay, so this is our so we have to solve this. So we can re-express this in terms of our equilibrium rise height. Okay, so if we scale, define dimensionless variables, so we define our Z star as our column length divided by the equilibrium height, so that's going to approach 1 as time goes to infinity, and the time okay, and we choose this one for mathematical expedience, then we get the following dimensionless equation. Okay, so we can integrate this. Using all of the tricks we learned in undergraduate calculus. Which I thankfully still teach, or I would have forgotten it all. Okay, so note we know in the long time limit Z is going to H, so Z star is going to 1. So we have 2 distinct viscous regimes. Okay, so in the early okay, so if Z star is much less than 1, we can expand this. Which tells us that, so substituting in here, okay, so we see that Z is going to go as the square root of time in the second regime. And if we redimensionalize, we get the following. Z equals sigma A cos theta over 2 mu t. And this is all to 1/2. So here we see in this early viscous regime, the the speed increases with surface tension, decreases with viscosity, as you expect. This is known as Washburn's. So this is still independent of gravity. And then we have the late viscous regime. So this is as we approach the equilibrium height, gravity is going to come into play. So I got this just by re-dimensionalizing Z and T, right? So late viscous regime, Z star is approaching 1. So here, so we substitute in here. Okay, and so as Z approaches 1, this term gets big. So this thing's order 1. We can throw it out because this term is dominating. Okay, so this gives us so we're getting now an exponential decay. And if we redimensionalize, okay, so where this tau is 8 mu h over rho g a squared. Okay. And if we two sigma cos theta over rho g a. Okay. Okay, so then we see this exponential. So if we summarize these three regimes, we can see three different stages. So we're getting an exponential decay in the latter stage. So we went from linear, the displacement of the front being linear in time, to square root of time, to exponential. So this is our Z, this is our H, and this is time. So it's basically a linear regime. And the square root of time. And then we have exponential decay. So this is basically the inertial regime. Early viscous. Right, viscous. Pardon me? Uh-huh. Yeah, you basically look, so what you do is you look at the master equation, you look to see when the two terms change in importance, right? So basically the inertial term will dominate the viscous term up till this time, right? So you can look at both solutions, the solution in here and the solution in there, and there'll be a crossover point, right? So you usually go back and check for consistency. Okay, so that's basically the solution. So notice that, as I said, I left some stuff out, but I thought it was relatively boring. There's a lot of work just to see what happens. It turns out at the very, very early times, you have to worry about the added mass, and that's here, but you just don't worry about that one. So I asked you guys to do the same thing with on the problem set for the case of plates. So the case of plates is similar conceptually and mathematically. We know that the effect is less dramatic for climb between plates because there's less surface energy being released, and you're getting a lot of surface energy when you have a cylinder. Okay, and so we've assumed here that you have this crossover. So this crossover point to viscous regime happens before you reach the equilibrium height. It's also possible for this inertial regime to spread, to go all the way to cover the entire rise. So basically the thing can get all the way to the equilibrium height while inertia is still important. And if it does, then it kind of goes, then it basically overshoots and you get these damped oscillations. Okay? Okay, so this time scale of rise is very quick. Okay, so in this case, the thing basically shoots up over, can go over the equilibrium height, and then it oscillates back and forth. And then those oscillations are then damped by viscosity. Okay? So I just want to highlight one regime which is quite important. So to understand the following, we need to be able to understand the following. Thanks. So we've just seen that there's an equilibrium rise height which is set by gravity, right? We know that the balance is between the curvature force and gravity, but they're also situated. You can also have horizontal motion in a capillary tube. So there we don't have gravity, right? So what's setting the equilibrium? Is there an equilibrium? Well, there isn't an equilibrium. So there you can see it going. So basically, it should go indefinitely, but it's going to slow down. And why is it going to slow down? Because you're getting the same rate of release of surface energy, right, which is all happening here, but this rate of surface energy is being combated by viscous forces along the length of the tube, right? So as the tube gets longer and longer, you expect the speed to go down, okay? So you can see the thing is grinding to a halt there. Okay, and that's exactly what happens and so this will happen whenever viscous stresses dominate gravity. So here, although gravity, it's in the orientation where gravity is important, it's actually viscosity which kills things. But it's the same business. So this is just a piece of paper, and again the rise speed decreases dramatically because the same rate of release of surface energy which is happening at the front has to overcome all of the viscous dissipation associated with flow wicking through the entire piece of paper. So this is simply one of the regimes that we've elucidated here. So we can, I'll just highlight it. Yeah, in this one, but yeah, it would. Yeah, you wouldn't see much difference though if you put the piece between it. No, very little, because the principal resistance is viscous. Okay, so let's just. This is what's called wicking. So wicking in a candle. So a candle wick. Wax wicks into the wick of the candle. Does the word wick mean anything to you in English? Wick. A candle wick. Because you're basically burning off the wax and fluid, and the wax is wicking into the wick. Right? Wick. A candle wick. You know, so candle? Candle.
That's a pretty wicked question.
Yeah, right. So this is our a candle, that's the wick. And so you basically have a flame which is burning off so you basically have melted wax here. And as you burn off the wax, more wax wicks up into it. Okay? So that's the wick. I was just trying to think of what. This is because this is called wicking. I was just thinking about its origins, but pavio. Isso? Okay.
So the melted wax will then go up the wick. Is that what you're saying?
Yeah, yeah. Okay, we've seen it in the viscous regime. We have this balance.
So if the wick is very long, the wick is probably going to burn down to a little height where sort of there's a max balance.
Yeah, that's right.
The heat of the flame,
Yeah.
melting the wax, and the wax needs
Yeah.
to sort of rise up.
Yeah, that's right, and replenish. That's right. Okay, so we've seen this balance. We have capillarity. So the question is, what happens if viscous stresses are much greater than gravity? Okay, that is to say, we can throw this guy out. And we saw, so this is obviously the case if we have a horizontal tube. We have an interface moving through here. And also in this, the paper towel. How do you say paper towel? Huh? Okay, so so paper towel. So the reason these problems are so important is there are a lot of things which are porous media, right? The ground is basically porous media. If you have some packed earth, it's sand and clay and what have you, and you basically have some microstructure which makes it a porous medium. So when it's in the vicinity of water, water oftentimes wants to go into it. So the ground flows are strongly influenced by capillarity. Okay, so the balance then, bin gravity, so we have, of course, this is just one of the limits of our general solution, but it's derived in a slightly different way here. And we again get Washburn's law, which expresses the motion of the front when there's a balance between viscosity and so it corresponds to our square root regime. So balance between so that was our early viscous regime, but that's what you get when the balance is between capillarity and viscosity. And I've highlighted it because it's important. Okay, let's take a little break. Any questions?